Alrighty folks, I'd like to welcome everybody to what's going to be a new project for me and a new series of ham-fisted and boring videos for everybody else to probably not enjoy too much, but there may be some comedy value there, so I reckon I'll give it a shot. So, have mentioned briefly in some of the previous videos that we're looking at a new project around automatic gearboxes. Now this particular one that I'm leaning against here is a ZF5HP24. This particular model is fitted to a lot of different cars, but the obviously make that we're interested in will be the BMW variant, which is what this box here came out of. Now, the goal of this project is to develop a electronic control system for the 5HP24 in particular, and probably some of the other ZF gearboxes and perhaps others that use electrically controlled solenoids to perform gear shifts. Now, you might say to me, well, why are we taking this particular project on? Well, there's some general reasons in or about. It's just something that I'm interested in and so forth, but there's one particular reason, and that is that this particular gearbox, the 5HP24, is fitted to a particular model of BMW that is going to be my next conversion project. And a little bit like the way in which I started the 5 Series E39 project by way of actually purchasing a gearbox and building the drivetrain before even looking for a car. This is what we're doing here with this automatic. Now the particular car in question only was manufactured in a reasonably small quantity, and an even smaller quantity still with a manual gearbox. So the automatic is pretty much where I'm going to be at for that project. So that being said, this kind of gave me a little bit of a shove that I needed to start investigating the possibilities of utilizing an automatic gearbox in an electric vehicle conversion project. Now, like a lot of relative newcomers to the scene, I shied away from automatics because of some of the perceived difficulties that they present, and some of the perceived lack of efficiencies that they generate in a vehicle drivetrain. So over the course of this video series, we're going to see whether any of that stuff is true or not. You're going to get to witness me screwing up a lot. So as I say, there may be some comedic value there in that from an audience perspective, but hopefully we'll get through some of these issues and find that we get a workable drivetrain out of this gearbox that we can put into a particular vehicle that is going to, in one sense, make a little bit of a departure from my usual philosophy with conversions to date, that you know, things are kind of, cost is the first concern. So we're going to be going away from that, and there'll be a lot of new things going on here. But the first step is to basically get this gearbox spinning with an electric motor attached to it. So that's what we're going to be doing now. We're going to walk through some of the initial steps that I've been looking at to make that actually happen. And we'll have a look then at the gearbox itself. We'll have a look at the electrical connections, the shifter, the hydraulic connections for the intercooler. We'll be looking at the torque converter, getting the adapter plate made, getting all the spacings correct. I have ordered a filter kit for this gearbox, so we'll be flipping it upside down and changing the filter and changing the sump gasket. So we'll have a look in there as well to see what's going on. One thing I have done is I've drained out the rather nasty gearbox fluid that was in this unit, so we'll be probably giving it a flush. We've got some issues around a particular grade of fluid that goes into this box as well, so we'll be looking at that. So we've got quite a lot to do. So as I say, the first step on this particular journey is to get ourselves a motor that will just spin the gearbox for me. Now I want to stress that the motor that we're going to see now is going to be coupled up to the box solely for the purposes of spinning it and letting me do bench tests. It is not by any way going to be the motor that will be ultimately coupled up to this gearbox that is going to turn the back wheels of this particular car. So I have a suspicion that when we get deeper into this and that I reveal the car and what I'm going to be doing to it, and it's going to I think it's going to make me two things: probably a pariah in some people's eyes, and maybe something a little bit better in other people's eyes. So we'll get started off. It's enough of me talking nonsense, and we're going to walk through now doing one of the possibilities that I've been looking at, to do a coupler to connect the flex plate to the motor shaft. So stand by for more. Okay, so what we're looking at now is a motor. This particular motor is a 10-inch GE, I believe, out of a Heister forklift that I basically stripped down, cleaned it up and gave it a paint job. As I say, the purpose of this is to give us a motor that we can couple up to the gearbox to get it spinning, and work through the development of the controller and so on without having to go to the expense of the ultimate motor up front. So it also lets me just run the thing from a 12-volt battery, and greatly simplifies that particular side of the development. Now this motor, as is fairly common with most DC forklift motors, came with a splined output shaft. So when I stripped the motor down, I took the armature out, obviously, took off the bearings and all that sort of thing, and went ahead and had a local engineering company turn down the splined portion of the shaft to get rid of the splines and make it a standard size of parallel shaft with a keyway. So it worked out that when they got below the minor diameter of the splines, that 35 millimeters was the first available size, and that's what they did for me. And I have to say they did quite a good job on that at a competitive price. So only other work apart from the cleaning and the paint job was to replace the bearings. They're just standard bearings. I believe it was a 6206 and a 6209. I got good SKF versions of those with C3 ratings, so I will probably use this motor for something else after the Gearbox project, so I thought it'd be worthwhile doing a bit of a refurb on it. And interestingly, as you might be able to see from the pole bolts here on the side of the frame, this is actually an interpoled motor, and I had a little bit of fun figuring out the connections on that, and I was putting it back together again, but it was quite educational in that sense anyway. So obviously that leaves us with a plain shaft, and we need to look at a means of connecting that shaft to the flex plate, which ultimately holds the torque converter and transmits drive between the engine, in this case our electric motor, and the automatic gearbox input shaft. So we now need to have a look at a means of doing that. Okay, so what we're looking at now is the flex plate, which is this big guy here, and it's made out of two parts actually, unlike a flywheel from a normal manual gearbox setup. So the flex plate is so called, I believe anyway. Now please bear in mind that I'm no expert on this stuff, so I'm pretty much regurgitating things that I've read about, so don't take this as being gospel. What we've got here is a two-part flex plate. Now obviously here in the center, this is where the bolts go that would normally attach that to the crankshaft of the internal combustion engine. Now obviously we don't have that, so we're doing something else. Now, I did mention that the flex plate is so called because it flexes like this, which is, I have to say, a little bit strange for me when I first saw it, because it came to me in two pieces and I couldn't quite figure out how this thing actually worked. So a little bit of research and a little bit of playing around. I had to put an arrow mark here because there seems to be only one way that this part sits on the flywheel section and lets the bolts then for the torque converter come through these four holes in the flywheel section. So that's how the torque converter bolts in from the back. So we have a flex plate, obviously, and we need a means to attach that to the motor shaft. Now, keep in mind this is an experiment, so we're looking at a few different options, and what I'm doing now may not ultimately be what we actually employ. And in fact, I'm pretty sure it won't be what we employ in the car, because if I did and I dropped the hammer on this, it'd probably fly into 1,000 pieces. But it's just to give me a bit of a feel on this, because the previous couplers that I've done for manual gearboxes have been all touchless couplers. So this is my first foray into any kind of flywheel setup, be that for manual or automatic. So, okay, so what I decided to do is to have a look around. Now 35 millimeters, as I said, is a standard size for taper locks. So what I did, in that for a minute, was I went out and I bought one of these jaw couplers. These are readily available and they're designed to couple two shafts to transmit drive. So I picked up one of these, and comes in three pieces actually. You have the two end parts that bolt onto the shafts, then you have a rubber kind of a donut guy that goes in the middle. That whole thing fits together and that's your coupler, simple as. But I had a somewhat other idea in mind for this one. So what I did was I came along and I took one piece of it, this piece here, and I started having a look at the diameter and the kind of meat section of the coupler. And I was having a look at it in relation to, get rid of that part of the flex plate so we might be able to see this a little bit better. I was having a look at it in relation to this diameter here and the locations of the fixing bolt holes, and I found that if I just sat it on top of the thing and just kind of moved it around until by eye it was kind of in the ballpark of where I wanted to be, that I was, that I had enough meat going around here potentially to actually bolt this flywheel component onto that. And obviously then it was a simple matter to get a 35 millimeter 1610 taper lock to fit in there and put that onto the motor shaft. Actually put it on backwards. Now the key issue here is if we just come along, obviously because there's no registering surface here and there's nothing to locate our flywheel flex plate, then I could have it all over the place here and it would be spinning around in all kinds of different arenas. So obviously this diameter is pretty much 35 millimeters. I got my calipers out and I measured 42.15 millimeters as the inside diameter of this box on the flywheel flex plate, whatever it's called. Anyway, so what I did then is I got a piece of steel stock on the lathe and I just did two parallel turning cuts on it. 35 millimeters here and about 42.05, 0.07-ish on this component here. And what that let me do was come along and turn my flywheel upside down and sit it on like that. Then come along, and I'm going to have to knock that taper lock back out, I would imagine, because it's probably tightened up a little bit on me. There we go. And I could then come along with my taper lock and sit it on top like so. And that meant then that my two components should be reasonably well lined up. And that let me then come along, and it's going to get ugly, and flip the whole thing upside down like that and get my locating punches. So I was able to use these holes, by the way, are just under 13 millimeters in diameter. There is one hole here that is this hole here is larger, and it was originally used with a dowel on the crankshaft because, as you might notice, along the periphery of this flywheel with these little teeth, obviously designed to cut people up and so forth, but there's two of them missing, and that's kind of indicative of a RPM pickup with a TDC mark. And if you have a look, which we will later on, at the bell housing of the gearbox, you'll see there's a little inductive pickup that looks at these teeth here and obviously picks up crankshaft position and engine RPM. So we then had a look at the bolts that came from the car engine, where this was bolted onto the crankshaft. So these are M12 by 1.75. These are M12 by 1.5, which is a metric fine 12mm thread. Standard M12 threads, I believe, are 1.75mm pitch. So we had to come along and get a tap and drill out. I just did my locating punches and drilled out two of these holes just for exploratory purposes to let us bolt down the two components. So we can thread two bolts in there like so and bolt the whole thing up. And I've just made my first mistake in that these bolts are designed to, they've got a shoulder on them, and the spacing on that shoulder will be designed to have the two sections of the flex plate assembly here, and I don't, so I'm going to have to go back and I'm going to have to put that in here now. So I told you there'd be lots of this stuff. So we need to go backwards. So flip it over. Take the taper lock section off, take the flywheel section off. Now I need to match up my two Marx Brothers. And there we go. Now we need to flip back over, back onto the locator device. And there's our 4 holes here now where the torque converter ultimately bolts to. Oops, that's just after falling off. Fit that guy, which means that it would have actually gone on over the piece of material that I had. Well, there you go. Another mistake. Hey, that's 2 on the first iteration, so I'd say that's pretty good going. I should probably tighten up that taper lock a little bit as well. Probably wouldn't hurt us. Let's have a little bit tighter, but we're just demonstrating here. So now, so there's my 2 arrow marks lined up, and if I take 2 of my bolts, I can fit one in here, one in here. With a bit of luck and a prevailing wind, this might actually work. So these are a 19mm, the average age of the combat soldier, and in this case the average size of a hex head bolt, which is rather strange because BMW tend to like 16 and particularly 18mm spanners as well, and unfortunately I've melted all of mine, so if anyone wants to donate an 18mm spanner to me, please do so. So there we go. So that lets me tighten up just 2 bolts there to see what actually happens. So in theory now I can remove that device, and in theory there is our assembly all set and ready to go on to the motor. So obviously these jaws can be chopped off, but I'm not doing any of that at the minute because I'm still kind of having a look to see how this is going to play out. So I'm going to go ahead and I'm going to sit that onto the motor and we'll give it a spin and see what happens. So stand by. Okay, so went ahead and fitted on the flex plate onto the motor shaft, just using my 2 bolts, and I just slot it on there. I just used a little 5mm hex key just to tighten up the 2 grub screws on the back of the taper lock, and just give it a little spin by hand. Seems quite happy. So this is it, first spin on a 12-volt battery. So fingers crossed. This could very well decapitate me, in which case I'm probably going to get way more views than normal, but I suppose I'll be dead, so it won't make that much of a difference to me. So here we go. Done. Everything actually works. Okay. Well, as an old friend of mine used to say, that's not bad for a bog man. Let's have a look and see if we've got any kind of run out going on there. Wow. Nothing visible. If you get a clock on it, I'm sure there'll be something, but just for a first outing, yeah, that's actually happy as a clam. Let's give her a bit of a close-up here on this. The decapitating machine is spinning away. And get a view there. You might be able to see, I'm not sure it's going to come out on camera, but not really anything visible to my eye anyway, and I've got a pretty good eye at this. If this thing was going to give me a bad hair day or so forth, I'd be able to pretty much see it, I think. So I'm really in the path of decapitation now. So there we go. Looks like we got ourselves a spinning flex plate. So I guess what we got to do is to put a few more bolts in that, just to make it a bit firmer. I'll probably only use 4 or maybe 6 bolts in the entire thing. As I say, this is not a permanent fixture. This is solely to let us have a look at connecting this thing up and running the gearbox to the point where I can actually start controlling it. So, looking good. So as I've been saying, this jaw coupler version that we're looking at is not necessarily going to be the finalized version of the coupler that we'll utilize on the car. Now, you might ask me why that is. Well, first of all, this is a cast iron construct. And we're going to be drilling, let's see how many holes this thing has. Actually, I never even counted. 1, 2, 3, 4, 5, 6, 7, 8, 9 bolts that have to be spaced around that. And they're M12 bolts. So we would be weakening that structure. As well as that, it's only a 1610 taper lock on this. So I would be concerned about the fact that it'd be cast iron with a lot of drills in it and a small taper lock. So what I'm probably going to be looking at, I've been having a very brief examination of this as well, will be something like this. Now this is a steel triplex chain sprocket, but unlike the 1610 taper lock that fits the jaw coupler, this uses a 2012, which is a much more substantial taper lock. But by far the most important difference between the two is that this chain sprocket is made from steel, and pretty tough steel as well. So if we can imagine drilling our holes, we'll have to buy a chain sprocket that has the right diameter. This one's close, it might work for some investigation. But a chain sprocket or something like this that has the right amount of meat on its periphery, and we can drill the holes and basically bolt the flex plate down to that, and that gives me that really nice taper lock to go onto the motor shaft for whatever motor it may be that we ultimately decide to use for the car side of this project. Now, I just wanted to mention one last thing here, just in the introduction, that kind of, in one sense, guarantees that even a muppet like me can actually make a go out of this. And that particular reason is that although this gearbox is electronically controlled, and this is the connection here for it, which we'll be going into detail with in future installments. Even if we've no electrical connections to this particular gearbox, it goes into something called fail-safe mode, and in one sense that nearly suits the electric vehicle application perfectly. In failsafe, park, reverse and neutral work as normal, but when you select drive, the line pressure goes to full and the gearbox stays in fourth. Now, fourth on this one is straight through, 1-to-1. So even from a testing perspective and getting the car moving, we don't need the controller at all. We could just bung this into the car, connect up the mechanical cable to the manual valve and drive it. Now, the one disadvantage from EV perspective is that the torque converter lock-up clutch does not operate. So, and we obviously can't shift out of fourth gear, but it is just an interesting feature of these particular gearboxes. I know other ones probably do the same thing or some variant of that, but I just thought it's worth mentioning. And so yeah, this is just a little intro today into the project, and we'll be getting some aluminium in soon to start looking at adapter plates, and we'll be getting the torque converter and the flex plate hooked up and getting the motor bolted up to the gearbox, and getting the thing spinning and filling it with fluid and changing the filters and blah blah blah. So stay with us folks, more to come.